Hello, so in our second lecture on simplified photolithography, we are going to discuss some fundamental definitions that you will require during your lithography experiments, and we are also going to talk about what is a clean room. So clean room is a place where you actually perform the photolithography experiments, because actually any microfabrication experiment, when you're trying to make something which is smaller than 5 micrometer, if you do it under your standard lab conditions, or if I try to do it in my office, what will happen is there are so many particles in the air which are actually larger than the feature sizes that I'm trying to make. And this dust or these particles, even the moisture, can affect my structures and the reproducibility of my fabrication. So I need to perform the experiment in a highly controlled environment, and that is why there is some facility created which is known as the clean room. We are going to learn what is a clean room. But before that, let's talk about some definitions. So we talked about cross-linking also in our previous slide. This is a property of a negative tone photoresist. Okay, what happens is when you expose it to the UV light, this chemically changes something into the material, and then the material converts into, it becomes harder by cross-linking. So how does that happen? These polymers typically have two things. One, they have certain functional groups that are very photosensitive. So that can actually, certain bonds, let's say, which can break when you have a small activation energy provided. So that is number one. And number two, you have something known as the photoinitiator. Now, in most cases, these photoinitiator materials, they may be some nanoparticles which are added, on top of the polymer. But in some cases also the polymer may be designed in such a way that this the job of the photoinitiator is basically to lose a proton, which can provide the energy for breaking that weak chemical bond that we were talking about. So it can, the proton can be provided by an external material, external photosensitive material, or it can be provided, maybe some part of the polymer itself can provide such a reaction, which is actually dependent on the intensity of the UV light that is provided to it. So now what happens when we expose this material to the UV light? Then a proton is generated. This proton goes and hits the weak bond. Let's say, for example, epoxy brand. I'm taking the example of an epoxy bond because this is the bond which is present in many commercially available photoresists, which are typically phenol formaldehyde resins, especially the negative resist that I'm talking about. So they have this epoxy bond which is broken by the proton, and now when the epoxy bond is open, then you have two dangling bonds or two free electrons which can further bond with another epoxy which is broken. So you have radicals and they then bond with each other. So your polymer basically looks like this. Polymers, you know that they have a lot of long chains, right? And they are randomly oriented long chains. The polymer looks like this. And now on the sides, you will have typically the epoxies. And when the photoinitiator opens the epoxy, it bonds with the neighboring epoxy sideways, and that is why it's called cross-linking. And this reaction then produces one more proton. So this is a chain reaction. So typically what you will do is when you expose the material to the UV light, then you actually initiate the reaction, and then that is why you need a post-exposure wake. That is where the reaction progresses or propagates, and at the end you will get something like this. You will have the same polymer but cross-linked. So it has all these. Now it is more like a big hard chunk of material, and that is what is known as the cross-linking process. Okay. Now, second thing is the viscosity of the resist and how it is related to the thickness of the film that you're going to fabricate. You know that this entire thing, it started with a thin film technology. When we talked about solar cells and so on, we were always talking about thin film. Now how thin is thin? In some cases, so typically films thicker than 1 micrometer are considered thin films, but in some cases even somebody may consider 5 micrometer or 20 micrometer film as a thin film. However, because it also depends on how large is your film and what is the final application. But in general, films that are like 50 micrometer or 100 micrometer thick, they are called thick films. They are still called films, but they are called thick films. Now, this is common sense that if you take a very liquid, like very low viscosity material, you put it on top of a wafer, then you will have a thinner film compared to a thicker material like honey or something like that. If you pour it on top of a wafer, then you will have a relatively thick film. So this is the same principle also in the case of photoresist. So when you go and you want to buy a negative resist, typically it will be available in different viscosities so that you can optimize the thickness of the film that you want to make. So what happens is there are resists that can give you up to 150 micrometer thick. So the 150 here is with the micrometer. 150 micrometer thick films, or even you can make one film and dry it and make another film on top of it. So that's how you increase the thickness of your film. Now, however, at some point you will not be able to cross-link it with the UV light till the end of it. So up to 150 micrometer films you can still work with, but when the films get thicker, then the UV light will get diffracted and it will not reach all the way to the bottom of your structure. So then also there is a balance. You cannot make very high structures using this photolithography process also. So now how do they make different viscosities of the polymer? By either changing the solvent or by changing the molecular weight or the length of the polymer chains. Okay, now you can see that it is the negative resists that come in different viscosities, and that is why they are typically used for making higher structures, while thin films are more in the case of positive resists, which are very thin structures. They are more like a more 2D structures, but with these negative resists you can make 2.5D structures, higher structures where you have the 2D structure, but the height there is a measurable height. You can control the height. Now, structures like MEMS are micro electromechanical systems, where you are sometimes where you are using the mechanical properties of a material to get an electrical signal, or the electrical properties of the material to get a mechanical system. So these are called electromechanical systems, and because they are micro scale, they are called micro electromechanicals. They are called MEMS. These kind of structures require a certain height. They are not always 2D structures, they are 2.5D. So in these cases, you are typically going to use a negative resist rather than positive. Okay, one more definition which is very important is known as the critical dimension. Critical dimension is nothing but the smallest feature size, let's say 5 micrometer in your case or 20 micrometer in somebody's case. That is the smallest feature size which you can make in that particular process, given the combination of the mask, of the resist, of all the parameters. In your certain experiment, the smallest feature size that you can make, that is known as the critical dimension. And that is the critical dimension of your fabrication. And remember that it needs to be done reproducibly, because sometimes you may end up getting a very small structure, but you may not be able to reproduce it. In that case, you will not call it a critical dimension. Okay, now as I promised, we'll talk about the clean room. So clean rooms are basically these facilities or the rooms where you have a lot of filters. In fact, very expensive filters which are running 24/7, and you also have positive pressure in the clean room so that the dust particles, if any, will go out of the clean room and not come inside. Now, the biggest source of contamination in these clean rooms is actually the human beings. Because when we go inside and when we breathe, or somebody's hair falls, or there is some skin particle or something like that, that is what actually makes the clean room dirty, so to say. And that is why when people go inside, they have to completely gown up. So I have a picture somewhere. Yeah, this is a picture of somebody in IIT Mandi clean room, and this person you can see is completely gowned up. This is not for his protection. This is for the protection of the clean room, because otherwise he will contaminate the clean room. And that's why it's important to take these measures, because these clean rooms are very expensive. Now, how do you measure how clean is the clean room? You will see how many particles that are bigger than 0.5 micrometer that are present. There are so many sensors in the clean room which are always sensing how many particles per cubic foot are present inside the clean room that are bigger than micrometer. The particles smaller than 0.5 micrometer, we don't have much control over it because the filters are not so strong that they can capture all the particles. But also the particles that are smaller than 0.5 micrometer are not so harmful for a process anyway. But bigger than 0.5, they are harmful for us. So this is what we measure in per cubic foot. 1 cubic foot, what is the number of particles that decides the class of your clean room. So if there is one particle in 1 cubic foot of your clean room which is bigger than 0.5 micrometer, then this is called the class 1 clean room. Similarly, class 10 clean room, class 100 up to class 100,000 clean room. Now, these clean rooms are extremely expensive. So, the most common clean rooms for research purposes is 1,000 or 10,000 class. Because it's very difficult, it becomes more and more expensive, exponentially expensive when you go for higher cleanliness. Here in IIT Mandi, if some of you want to perform any experiment, we actually have a very nice class 100 clean room, which is actually a very expensive facility. Class 10 clean rooms you will only find in in companies where they are fabricating chips for the computers and so on, because those are extremely expensive. Most of the class 1 and class 10 clean rooms are actually human free. So all the machines everything is automated and the machines are doing the job. So those cannot be used for research purposes or student learning purposes anyway. Okay. So lastly, for performing the photolithography under the UV, because you also need one more parameter, you need UV free environment, because you're going to use the UV light only on the part of your material that you want cross-linked, or you want to use the UV light for processing. So what you also need is UV free light. So inside the clean room you will typically have something called a yellow room, or at least students, or at least I used to call it a yellow room because it looks yellow. It's like a yellow light room. And that room basically has filters for UV in the lights, and that's why you can perform your photolithography experiments there.